This video is entirely on differentiability. I have made a video on continuity already, so this is a separate one on differentiability. Now, if you remember, let me just recap a little bit from just hold on. Yeah. If we do a quick recap of the definition of a derivative of a function at say derivative of a function y equal to fx at a particular point, say x equal to c, belonging to the domain of the function, as done in class 11. If you remember, first principle, we called it first principle. So we said that uh, derivative of the function at a, that is f dash a, was limit h tends to 0 f c plus h minus fc by h. So the derivative of a function at a point c in its domain was defined like this. We called it first principle, the definition. But then there was a very important phrase added to it, and that was if it exists. So in class 11, we did not pay much heed to this portion, if it exists, because you were given sums like find the derivative by first principle. So obviously it exists, so that is where the sum was given. But in class 12, we will have to check whether given a function and given a point in its domain, whether a function is differentiable at that point or not. That is, whether this limit exists or not. This particular limit exists or not. So that is what we mean by checking differentiability of a function. If it is differentiable, then only then we can say that the derivative exists, and then we write the definition of the derivative as this. So first we have to check whether this limit exists or not. And you know from the concept of limit that the limit always exists at a point if and only if the left hand limit and the right hand limit at the same point are equal. Only then the limit exists. So, see, extending that concept to this limit, that is f dash day also, we can say that this particular limit, that is this one, this will exist only if we break it into its left hand limit, right hand limit, both exist, then the limit exists. So this brings us to the definition of differentiability. So this is just a bit of introduction. So how do I define definition? So I'm not writing all those things, c, f, x, that is obvious. So I simply write that f is differentiable at x equal to c if left hand derivative, that is, we break this above limit into two different limits, left hand limit and right hand limit, and the left hand limit we call left hand derivative. And so left hand derivative is limit h tends to 0 from the left, if c plus h, rest of the things remain same, by h, this is left hand derivative, equal to the right hand derivative, that is limit h tends to 0 plus fc plus h minus fc by h. So if these two limits, left hand limit and the right hand limit, which are termed as left hand derivative and right hand derivative, if these two exist and they are equal, they are equal, if they are equal, then we call that f is differentiable at x equal to c. So in that case, so f is differentiable if this happens. In that case, we write the derivative. The derivative sorry, is f dash a equal to, some different symbols are also used. I'll write that. Limit h tends to 0, fc plus h minus fc by h. We also write the same thing, that is derivative of f at a. Instead of writing using this symbol, we can also use f1. This is dash f1 at a, or we can write dy dx at x equal to a. Okay, by mistake I wrote here a and here I wrote c. Extremely sorry. And this should be c. These are all c's. We are finding the derivative at c. Okay, so at c, fc. This is also c. So this is c and this is c. X equal to c. Okay, so that is the main concept of the chapter differentiability. So please remember one thing that is very, very important. Unless you prove that the function given is differentiable at the point C, you cannot write the derivative. You cannot write the derivative, that is f dash c, you cannot write at all. So that's the main thing. Okay. Now, next important thing that we have to understand is the relation between differentiability and continuity. Okay, before going into that, let me stress some points on this differentiability with a different color. The points usually where students make mistake. Now, check one thing. I should have written here. Actually, you already know what is age. That's why I just didn't write it here only. When we were recapping, when I first use the word symbol age, you know that age. What is age? Age is a very very small positive real number. Real number. That means basically what we mean is that uh, c minus h and c plus h. This is actually a very small neighborhood. This is called neighborhood. Neighborhood. Very small neighborhood of C. Okay, so now next important point is relation between continuity and differentiability. This is a very very important point. Now, before going into the relationship, let us do again a very small recap of the definition of continuity. That is, fx is continuous at x equal to c if limit x approaches c from the left, that is left hand limit, equal to x approaches c from the right, fx equal to functional value fc. That is, if we combine these two together, then limit x tends to c fx equal to fc. So in a more compact form, this is the definition of continuity. Now in this definition, if I say put let, suppose this definition I number it 1. Now let one second. I want to give you an alternative definition. You know all this. Let x equal to c plus h, where h is a very small positive number. Very, very small positive number. That means as x approaches c, I can say from this relationship, as x approaches c, h approaches 0, right? So we the alternative way of defining continuity, that is alternative way of 1 will be that if continuous at x equal to c, if limit here, but at me what I'm trying to do is changing the limit from x to h. That is, here it was x approaches c, so here we have seen that is as x approaches h approaches 0, so h approaches 0. So instead of fx, so you now have x plus h, that is c plus h, x is c plus h from here equal to fc. So actually 1 and 2, what I'm trying to say is 1 and 2 are equivalent definitions of continuity. Both mean the same. Now why did I do the second definition? The first one is enough for doing sums and all that. I did the second one because it is going to help me now when I do the next portion. Now, what is the relationship between continuity and differentiability? Now, differentiability is a much, much stronger condition than continuity. That is, what I mean is, differentiability always implies continuity. That is, if a function is differentiable, it will be continuous. But converse may not be true. May not be true. So obviously, when I want to show differentiability implies continuity, this requires a general proof because it is always true. But when I prove the second part, I will give a counterexample. So let us prove first part, that is differentiability implies continuity. So let f be differentiable at x equal to c. I'll try to do it a little faster now. So that is f dash c exists. I told you if it's differentiable, that is derivative exists. So f dash c exists, and we also know that this derivative is given by, according to the formula first principle, h tends to 0, f c plus h minus f c by h. Okay. Now, now, now I'm making an independent statement. If c plus h minus fc. I'm just choosing this expression. Now this can be written as, see how I'm writing it, okay? I'm just giving a bit of rest to my voice. I can write this y because h is not equal to 0 as h approaches 0. So I can divide it by h and multiply this with h. So fc plus h equal to this. So now taking limit h tends to 0 on both sides. So what do I get? Limit h tends to 0 fc plus h minus fc. So that's the left hand side. This one, limit equal to limit h tends to 0. Now we take the limit from the right hand side, that is this portion, but we split it into two limits from this multiplication sign. So h tends to 0, fc plus h minus fc by h into limit h tends to 0 h. So obviously this portion is 0, so the entire thing becomes 0. So from here, limit h tends to 0 f c plus h. Now this fc is constant, so the fact that h is approaching 0, that is h is a variable here, has no effect on the constant fc. So it remains fc and that goes to the right side fc. And this implies that f continuous at x equal to c by the alternative definition 2 that we have done earlier. So what we saw is, one second. So this is actually, I should have written here something which I actually skipped. I think I should write here. This portion, limit h tends to 0, this portion, this is f dashed c, right? From here, from 1, from 1. And this second portion is 0. So ultimately that is 0. So this shows that if a function is differentiable, if we differentiable at x equal to c, then it will be continuous at x equal to c. So differentiability implies continuity. Now the converse may not be true. For that we will take counter example. Number 2. So here we want to take examples, counter examples, uh, to show that a function, what do we want to show? We want to show that a function is continuous but not differentiable. So here we want to give examples of functions continuous but not differentiable. The most common function that you have done is, so just let me give the examples. Fx equal to mod x. So in this case, we know that if I just quickly draw the graph, then you know fx equal to mod x is this. Now, this function fx equal to mod x, it will be differentiable everywhere. This function will be differentiable everywhere in R except x equal to 0. Okay, so just remember this thing, that if a function has a corner like this, a corner either like this or like this, these are corners. Whenever the graph of a function has corners like this, the function is never differentiable at those corner points. So obviously here at x equal to 0 is the corner, so it won't be let's check that it is not differentiable. First of all, it is continuous, that you have already done in the continuity part. Also, continuity is obvious from the graph, but that it is not differentiable, that let me check once. Okay, so first let us check what is left hand derivative. Left hand derivative is, remember, we want to check at 0, so our c is 0. So just blindly follow the definition of left hand derivative. Limit h approaches 0 from the, there is no change, this is always fixed for left hand derivative. H approaches 0 from the left. Then you have if c plus h, your c is 0, so 0 plus h minus f0, that is fc, by h. This is my left hand. So first always write the formula, then plug in the value. Now if you look at the function, if we deconstruct the function a little bit, then what do you get? It is plus x when x is greater than 0, 0 when x equal to 0, and minus x when x is less than x. So you know that this is the definition. Now h is approaching 0 from this. This is very important. Please try and understand this very carefully. H is approaching 0 from the right. Now h, what is h? H is when I say that h is approaching 0 from the, that means h is a number which is very close to 0 but is on the left side of 0, but is on the left side of 0. That means h is somewhere here. Here h is approaching 0 from the left. That means h is here. That means this indicates h is negative. This part is very important. Again, I am repeating. Here, the limit says h approaches 0 from the left. So, where is the h? Where are the values of h lying? They are lying exactly in this region. What is the region? It is very, very close to 0 but on the left side. That means, in other words, h is negative. Now, if h is negative, then we can say if, sorry, 0 plus h, this expression, that is whatever you have here, this is negative. And then the third branch of the uh, function follows actually. When I, after this, what we have to plug in the values of f0 plus h, that is fh and f0. So what will be the value of f0 plus h? If I want to put the value, I have to determine, right, which branch I have to choose, and that depends on whether 0 plus h, that is h, is positive, negative, or 0. So this fact tells me that if h is negative, that means my third branch will be active. So if 0 plus h, so from here I can say if 0 plus h, which is fh, will be, according to definition of mod x, minus h. So third branch is here. Third branch is being followed. So this becomes limit h tends to 0 minus, this is minus h, and f0 is 0, we know that mod 0 is 0, so by h, so that is minus 1. So left hand derivative is minus 1. So remember that this fact that h approaches 0 from the left helps me. This minus sign is the direction where h lies, whether it is on the left side or right side. So this minus sign actually just helps me to choose which branch of the function should I take. That is the deciding factor of this h approaching 0 from the left. Okay. Now, if I want to calculate, now let's calculate right hand derivative. So right hand derivative, again write the formula blindly. H approaches 0 from the right, f0 plus h minus f0 by h. Again, this time what is happening? Where is h lying? It is approaching 0 from the right. That means h is somewhere here. H is here. That means, in other words, h is positive. H positive. And if h is positive, then If 0 plus h is plus 0 plus h, that is fh. So according to the definition of mod function, h tends to 0 plus, this is, that is, this time my first branch will act. That is 0, since 0 plus h, that is h is positive, so it is plus 0 plus, so it is plus h, and f0 is 0 by h, so that is 1. So what do we see here? Therefore, left hand derivative not equal to right hand derivative. So that implies f not differentiable at x equal to 0. That means for this function, f dashed 0 does not exist. Does not exist. So though it is continuous, but mod x continuous over whole of R, and hence at x equal to 0 also. So this is one counterexample where the function is continuous everywhere and not differentiable at only one point, that is 0. Now, in relation to this, if we check similar to such similar functions, that is fx equal to, say, mod x plus some k, sorry, where k belongs to R. So in that case, I think I told you already that if you have a plus k here, then the corner lies at minus k. So in that case, the function is like this. So that means the point where derivative won't exist is here. This is the corner. For such function, this is the corner. And that means in this case, if not differentiable at x equal to minus k. Similarly, if you have a function like this, fx equal to mod x minus k, where k is any real number, in that case, your graph will be, if you have a minus here, then the corner shifts to plus k. So the graph is in that case like this. So your corner point is here. That means in this case, f not differentiable at x equal to plus k. Uh, in the above examples, actually, I tried to give you an intuitive idea through the graphs of the functions, uh, the counter examples, that is, examples of functions which are continuous but not differentiable at certain points. So, one intuitive idea is that if you find a corner, like I've written here, so this type of corners, if you have, a function will not be differentiable there. Now, there is another intuitive idea that helps us to determine without actually calculating, that is, uh, a function f will not be differentiable at a particular point c if slope of tangent at that point is not finite. Now, what do I mean by this? Say you take this graph, this graph. This is the origin. Now, at the point 0, at x equal to 0, the tangent is y dash. That is the y-axis itself. And we all know that slope of y dash not finite, undefined. That means If you have a curve like this, then this the point where the curvature of the function changes, that point will not be will be a point of non-differentiability. So if I want to combine both the factors, that is corners and this curve, and draw one single diagram, then intuitively, if you see a function which has a graph like this, then more or less you can say intuitively where the function won't be differentiable. Say my graph is like this. That means corner, corner, and more approximately here, the curvature of the graph changes. So these are the points A, B, and C. Because at C you see the at the point C, this is the tangent. This is the tangent which is parallel to y dash and hence not defined. So these are the points where the function won't be differentiable. So this now there is another uh, interesting example. See, in the above examples, that is ABC, I've shown you functions which are continuous everywhere and differentiable at one point. That is finite number of points. It could be 1 point, 2 points. Right. But now I'm going to give another example where the function is continuous throughout R, over the whole of R, but it is not differentiable at infinitely many points. So, what am I doing? Say first let me take fx equal to sin x. Now you know that graph of sin x is like this, sin 0 0. So this way it goes. Here also same thing, and of course uh, this is the graph lies between 1 and y equal to 1 and y equal to minus 1. So this is sin x. Now what I am doing is, instead of taking fx equal to sin x, let me take fx equal to mod sin x. Now what I am doing essentially is, my function, that is the value of y, cannot be negative. That means there will be a change in the pattern of the graph. What will be the change? Let's see. The change is something like this. Remember, there cannot be anything below xx dash because y will be positive. So xy, okay. So now the graph will be like this. So where, uh, suppose I number it 1 and this as 2. Now in figure 1, wherever y is positive, no change. So it remains positive. But wherever y is negative, that is this portion, then due to the mod it becomes positive. So it becomes like this. Again, next portion is positive, remains like this, and then again the negative portion becomes positive. So this is how, just by putting one mod, the value of the the nature of the graph changes like this. So this way it goes on. So what are the points where it won't be differentiable? Obviously, there are infinitely many corners in this graph, and all these red points, these are the points where it won't be not differentiable, not differentiable. Infinitely many such points. Okay. So intuitively, we can, by looking at the graph to some extent, we can say that it is at a particular point it is differentiable or not. Now next, let me just check the points, the system of points where we're using. Yes, relation between continuity and differentiability, that was point 2. Now we go to point 3, that is properties of differentiable functions. So here, as usual, like what we have done for continuous functions, here also you have the same. That is, if f and g are two functions and they are differentiable, then we can say that, um, okay, so if f, g are differentiable at x equal to c, then number one, f plus minus g, that is addition as well as subtraction, the new function that you get, that will also be differentiable at x equal to c. The product function fg again will be differentiable at x equal to c, and the quotient function f by g, of course g cannot be 0, is also differentiable at x equal to c. So this is all about theory of differentiable functions. Now we come to sums. Let us do some sums. Okay. Now I'll try to do the some of the board problems which usually come. First, let me do this sum. This was a 4 mark sum in the year 2015. Okay. So now we come to sums. Here, fx is defined as x minus 1 plus x plus 1, x belongs to R. Show that f is not differentiable at x equal to minus 1 and x equal to 1. Now, when the sum says show that, obviously we have to show it from the definition, but already from intuition you know that mod x minus 1 will have a corner at plus 1 and x plus 1 will have a corner at minus 1. So at these two corners, the function cannot be differentiable. So this is an example of a function which is continuous over whole of R, but not differentiable at 2 points. So similarly, if you keep on including the mod portion, say another mod x plus 3, then that will give you an example of a function continuous throughout, but not differentiable at 3 points. And of course, I've already given you not differentiable at infinitely many points. Anyway, now here the domain of the function is given as whole of R. So remember, in continuity we had done a similar sum, but there it was given x belongs to minus 1, 1. But here no such thing is given. The whole of R is the domain. So in that case, first and foremost, we have to redefine the function fx and divide my R, that is real number, the whole of domain, into intervals according to the definition of the function. So first let us redefine. So you know already I have told you that individually make the expressions within the mod 0. So you get the points where the branches will change, that is x equal to 1. Similarly, x plus 1 equal to 0 will give you x equal to minus 1. So that means minus 1 and 1. That means you are dividing the entire domain into three intervals: minus infinity to minus 1, this portion, minus infinity to minus 1. Let me take open interval for the time being. And then you have minus 1 to 1, and then you have 1 to infinity. So these are the three intervals. So let us see how the function behaves in these three intervals individually. So fx equal to, first if you take a point here, say minus 2. If you take minus 2, then what happens to fx? Minus 3, this is negative, right? X minus 1, this is negative. So what I mean to say is, if your x is here, then your x minus 1, x itself is negative. This whole thing, this x minus 1 whole thing, is becomes negative. So when you open the mod, then mod x minus 1 will be minus of mod x minus 1 according to definition of modulus. That's what I'm trying to say. Whereas mm, uh, same thing happens with the x plus 1 also, because here also you can see x plus 1, because your x is just on the left, I mean just not just, it is on the left of minus 1, so it is less than minus 1. So if you take this is minus 2, then this whole thing is again negative, this whole thing is negative. So when you remove the mod, the minus will come. So ultimately when I redefine the function, it is, for the first interval, it is minus of x minus 1 plus minus of x plus 1, that is equal to minus 2x, right? X minus x x less than minus 1, it is sorry, minus x minus 1, right? Minus x minus 1 minus x. So minus x 2x, right? So this is when x is less than minus 1, that is this interval. Now what happens when x is in minus 1 to 1? If you calculate it similarly, you will see that in this case, when x is here, in this case, your x minus 1 is negative, but your x plus 1 will be positive. So accordingly, the function redefinition becomes minus x minus 1 but plus x plus 1. That means it is just 2 when x lies between minus 1 and 1. And when it is greater than 1, then both the greater than 1, so suppose your x is here, x is suppose here, that is 2. So in that case, both are positive, right? Both are positive. So in that case, it is x minus 1 plus x plus 1. So that is 2x when x is greater than 1. So ultimately, my definition of the function is this. This is the definition of the function. And what happens at the points minus 1, 1? Obviously, you can see from the definition, if you put minus 1 or 1, then suppose you put x equal to minus 1, then this portion vanishes. And this becomes, let me write it here, when x equal to minus 1, what is my fx? Fx equal to, this vanishes and this becomes mod of minus 2, that is 2. When x equal to 1, then fx equal to, when this portion vanishes, this vanishes and this becomes mod 2, that is 2. So at these 2 points it is 2. So you already have 2 in the second branch. So you can include the equality here, because we have seen just now that When x is minus 1 or 1, then fx is 2. So I'm including these two values of x in the middle branch. So now I'm all ready to check the differentiability at these 2 points because we have redefined the function. Okay, so now that we have redefined the function, let us check the differentiability at the 2 points minus of 1 and 1 separately. So differentiability at x equal to minus 1. Okay. Here, let me just draw the number line once again. This is minus 1. So we are checking at this point. So first we'll calculate left-hand derivative. I told you blindly write the definition. So limit, it is always h, approaches 0 from the left, then f, the point where you are taking, that was c in our general definition. So here it is minus 1 plus h minus f of minus 1 by h. So that is the definition. Now you have to, the next step has to be done very, very carefully. Because you see, this is okay, let me write it, h tends to 0 from the left. Now what will be the value of f of minus 1 plus h? So when x is minus 1 plus h, what is the functional value? So I have to choose from one of the three branches. I have to choose from here. How do I know which branch is going to be active? Now, listen carefully. What we do is, here h, this is very important, h approaches 0 from the left. So where is my h? Okay, I have to write the 0 also. Here it is 0. So h is approaching 0 from the left. So h is somewhere here. Here is h. That means h is very, very close to 0, but on the left side of 0. That means my h is negative. If h is negative, then this implies that minus 1 plus h, remember h itself is negative, so minus 1 plus h, so suppose h is minus 0.5. So minus 1 minus 0.5. That means what is happening? It is becoming less than minus 1. I hope you understand this portion. Because h is negative, if you have any problem in understanding, take an example. Say h is minus 0.2. So if you replace here, minus 1 minus 0.2 is minus 1.2. Minus 1.2, where is minus 1.2? Here. So if this is h is minus 0.2, then minus 1 plus h is here. That is minus 1.2. So that means definitely less than minus 1. And less than minus 1 means I have to choose the first branch. So h determines which branch you will choose. Now the role of h is done. Now you simply have to, now that you know the first branch, you have to follow the definition of fx according to the first branch. So what is that? That is minus 2. It is minus 2x. So minus 2, instead of x you have minus 1 plus h, right? So that is the first part, minus 1 plus h. And f of minus 1, you can see from the second branch here, x equal to minus 1, it is 2. So minus 2 whole divided by h. So this is how you calculate the left-hand derivative. So if you calculate this, what is the value? It is coming out to be minus 2. So your left-hand derivative is minus 2. Now let us calculate the right-hand derivative. Right-hand derivative will be, again, write the formula. h approaches 0 from the right, f of minus 1 plus h, no change here, by h. Okay. So now what is happening? H is approaching 0 from the right. So where is my h? My h is here. Here is my h. That means my h is positive, which implies that minus 1 plus h is greater than minus 1. That means I will choose greater than minus 1. I will choose the second branch of the function. So second branch is 2, just 2. It's constant. It doesn't depend on the value of x at all. So, so this is equal to, uh, so it is just 2 minus 2, limit h tends to 0 plus 2 minus 2 by h, so that is 0. So finally what do we see? Left hand derivative not equal to right hand derivative, hence f not differentiable at x equal to minus 1. So this is part 1, and part B will be similar, so I leave it for you. Just proceed in the same way. Differentiability at x equal to 1. Okay, so that means here, if this is your real number line, suppose you have 1 here and 0 here. So when you calculate your left hand, I'll just leave the answer here. You can do the calculation because it is exactly similar to the first part. The left hand derivative will come out at 1, it will be 0, and right hand derivative will be 2. Okay, and remember here, where is your h line? When you are calculating left hand derivative, h approaches 0 from the left, that means here. So for left hand derivative, your h is here, so that means h is negative. And when you are calculating right hand derivative, h is here, that is this portion. So accordingly, you will choose the branch of the function. Okay, so you can finish this sum. So here also you see it is not differentiable. Now, this was sum number 1. Okay. Sum number 2 is a very similar sum. That is, you can see fx equal to, instead of having 2, you can take 3. Say x minus 1 plus x minus 2 plus mod x minus 3. So you can try this on your own. You have to show that. So this is, I was telling you before that the example of a function where, because it is ultimately a polynomial function, it will be continuous over whole of R, but it won't be differentiable at exactly 3 points. That is 1, 2, and 3. So show that f is not differentiable at x equal to 1, 2, 3. So this sum is just an extrapolation of the previous sum, but you can do it as a practice, nothing else. Okay. Now let us discuss a little bit about box function also. Fx equal to box x. Now whenever we discuss box x, obviously the graph is very important. So let me just keep the graph here on the right side. Let me divide the intervals of the domain. You know, for boxes, the domain is entire R. So we divide the interval like this. So 0 to 1, and then 1 to 2, and then 2 to 3, so on. Here it is minus 1 to 0, and then minus 2 to minus 1, so on. And the graphs are like this. from 0 to 1, this is the graph. And then here it is, this is, okay, let me first finish this. And the graduations on the y-axis is, this is 1, this is 2, this is minus 1, this is minus 2. Okay. Now we want to show that actually uh, what are the properties of box X? Here f is discontinuous and not differentiable at all integral points. Integral points. Okay. So if is discontinuous at the integral points, I'm not going into that because that continuity we have done, and I believe you can do it very easily. And this type of discontinuity is called jump discontinuity, which cannot be removed, right? So we'll discuss only the second part, that this is not differentiable at the integral points, right? Okay. So see, there are infinitely many integral points. So obviously we are not going to choose the individual integral points and show. So we'll do it generally. So let C be any integer. So we want to, what do we want to show? We want to show that if not differentiable at C. This is what we want to show. That means your C can be 1 or 2 or 3 or minus 1 or minus 2, anything. Now, left hand derivative. Limit h approaches 0 from the left, f c plus h minus fc by h, right? Now, let's see. C is any integer. Now, for the sake of understanding, you can choose C to be, say, 2. Let us choose that this is my C. This is my C. So, whatever argument I give here is, it holds good for all the integers. I'm choosing 2 because it will be easier for you to see. That is why. Now, what happens? When h approaches 0 from the left, then your h is here. Here is your h, right? Here is your h. That means h is negative. Okay. Now, if h is negative, then c plus h is less than c, right? And you know that for a box function, whenever you choose an integral point and check what is the value of the function just to the left of that integer. For example, here I have chosen 2 as my c. This is my 2. So c plus h is less than c. So c plus h is somewhere here. And what is the value of the function? It is 1. That is, it is 1 less than c. The value of the function is constant. And that constant value is what? 1 less than your c. Your c is 2, so the value of the function is 1. Had your c been 3, then to the left of 3, the value of the function would have been 2. That is 1 less than 3. So that is how box function works, right? So once you understand that, so we just put it here. Limit h tends to 0 from the left. So fc plus h, just now we say that it will be 1 less than c. So it is c minus 1. And now what is the value of the function at the integral point? If you see at the integral point, say for example at the point 2, then that is 2. For every integer, it is always the same uh, integer, right? So your box function at c is c divided by h. Okay, so limit h tends to 0 minus, so that's minus 1 by h. So this limit obviously does not exist. Remember in class 11 we had done that if the numerator is non-zero and the denominator tends to 0, then the limit does not exist. So left hand derivative does not exist. So from here itself you can say that it is not differentiable. But still we are going to go ahead and find the right hand derivative also. So right hand derivative is limit h tends to 0 from the right, fc plus h minus fc by h, that is equal to limit h tends to 0 from the right. Okay, that means h is positive. So c plus h is on the right side of the integer c. So for any integer on the right side, the functional value is the value of the integer. For example, on the right side of 2, box 2 is 2. On the right side of 1, box 1 is 1. Similarly, box fc plus h will be c plus h, and box c is always c. So it is h by h, so that is good. If I didn't mistake, let me see if c plus h is positive, so c plus h, if c plus h positive, c plus h is on the right side, so 2, yeah, yeah, so that's 1, right? So in fact from here we can, right, left hand derivative does not exist, so here we can conclude that box x not differentiable at c, and hence all integers, because c was arbitrarily chosen from the set of integers. So now this function is defined as x when x less than 1, 2 minus x when 1 less or equal to x less or equal to 2, minus 2 plus 3x minus x square when x greater than 2, and it is given that no, it is a RTP. You have to show that f not differentiable at x equal to 1 but is differentiable at x equal to 2. You have to show this. So I'll leave this as an exercise for you, and if you have any difficulty you can let me know, then I can discuss it further. Next, fx equal to x box x when 0 less or equal to x less than 2 and x minus 1 into x when 2 less or equal to x less than 3. This is how fx is defined, and the question is f differentiable at x equal to 2? Let's check. Okay, so 0, 1, 2. So h is approaching 0 from the left, so h is negative. So 2 plus h is less than 2. That means this region less than 2. And the functional value for the left hand side of 2 is 1. Oh, okay, no, sorry, I'm really sorry. Actually, yeah, box 6, what is, let us find it separately here. That is 2h negative. That means 2 plus h is less than 2. That means first branch will act here. Therefore, if 2 plus h equal to 2 plus h into box 2 plus h. Okay, so 2 plus h. Now, what will be box 2 plus h? Now, since h is negative, 2 plus h is less than 2. That means 2 plus h is lying here less than 2. So box 2 plus h is, you know that if you recall the graph once, it is like this here and then it is like this, right? So that is 1. Just left to the 2, it is 1. So this is 1. So that means it is 2 plus h. Okay. So let me put it here. If 2 plus h is 2 plus h. And of course, what is f2? You can see when x equal to 2, here, the value is 2 minus 1, that is 1 into 2, 2. So this is 2. Whole divided by h. So that is equal to 1. Now let us check the right hand derivative. Limit h tends to 0 plus f2 plus h minus f2 by h. So h is positive, so 2 plus h is now this here, 2 plus h, and for this region the value of the function is 2, right? So this is, sorry, limit h tends to 0 plus 2 minus 2 by h, that is 0. So your right hand derivative is 0. So left hand derivative not equal to right hand derivative. F not differentiable at x equal to 2. Now, next sum is a little different. Fx plus y equal to fx into fy. It is given for all x belonging to R. Fx not equal to 0 given. Derivative of the function at 0 is 2. All these are given. At p if dash x equal to twice fx. Now, let's start from here. Now, what is f dash 0? So obviously when it says f dash 0, that means the function is differentiable at 0. That is left hand derivative equal to right hand derivative, that is equal to the derivative at 0. So that's important. So first principle, we know that f dash 0 is limit h tends to 0, f 0 plus h minus f 0 by h. Okay. So this is given to be, let me write it here, this is given to be 2. Okay. So now we apply this property here. We apply this property here. So from this we get limit h tends to 0, f0 into fh minus f0 by h equal to 2 from the given property. Now let me take f0 common. So I'm left with fh minus 1 by h. Now we alright. So this f0 comes out of the limit, right? So that means I can write so this implies that 2 equal to 0 limit h tends to 0 h minus 1 by h. So 2 by f0 equal to limit h tends to 0 h minus 1 by h. So suppose this is number 1, this portion. Now we have to show f dash x equal to twice fx. So let's start with f dash x. So according to definition, it is h tends to 0 fx plus h minus fx by h, that is equal to, proceeding as before, limit h tends to 0, applying the given property fx plus h is fx into fh minus fx by h. Again same thing we are doing here, h tends to 0, taking fx common, It is fh minus 1 by h, that is equal to fx. Fx is a function of x, so approaches 0 will have no effect on this, so it will be limit h tends to 0 fh minus 1 by h, so that is fx. Now this value, this portion we have already calculated earlier from 1, right? So that is 2 by f0, 2 by f0 from 1. Uh, let us see what is the value of f0 separately. Let us see here what is f0, because in the sum you see f0 is not given, right? So any fx can be written as f of x plus 0, that is fx into f0, right? So from here uh, we can from here we can write that f0 equal to 1. Why? That is, you are dividing both sides by fx. Since fx not equal to 0, it is given. That is why we could cancel fx from both sides. Cancel means you are dividing. So the value of f0 is 1. So now we put this value here. That means it is twice fx. Since f0 is 1. So that is precisely what you had to prove. That is, f dash x is twice fx. 6. There is one more sum which is a little different from the others. I want to do that and then finish this video. I'll try to do it very quickly. Given if differentiable at x equal to 1. Your job is to find out the values of a and b. Okay. Now it is differentiable. So LHT equal to RHT. So let's first find out what is LHT. So I'm not skipping the definition here. H tends to 0 minus. Okay, let me write it. So it is 1 plus h minus f1 by h. That is limit. So okay, so h is negative. H is negative means 1 plus h is less than 1. That means first branch will act. That is, if for calculating f1 plus h, we have to consider the first branch. Why? Since h is negative, which implies that 1 plus h is less than 1. Okay. So now if I apply the first branch, then it is 1 plus h whole square, 3, 1 plus, simply replacing x by 1 plus h plus a. So this is f1 plus h. And now minus f1. Here you see when x equal to 1, again the first branch acts. So this time just put the value of x equal to 1 in the first branch. So it is 1 plus 3, 4 plus a. So it's 4 plus a minus 4 plus a whole divided by h. So if you calculate this, then you will get the value 5. I'm just skipping the steps here. Calculation you can manage. Now right hand derivative, h tends to 0 from the right. So f1 plus h. So this time 1 h is positive, so 1 plus h is greater than 1. So second branch will lay here. So b into 1 plus h plus 2 minus f of 1 is still the same, that is 4 plus a, 4 plus a whole divided by h. So if I simplify this, it is limit h tends to 0 plus. Now we come to a very interesting part. bh minus 2 minus a by h. Now this portion bh by h I'm separating. So h's will cancel, it will become b, so b comes outside. And the rest remains a function of h, that is b minus 2 minus a by h. Now listen to this part very carefully. It is given that if differentiable at x equal to 1, I think yes. So that means left hand derivative equal to right hand derivative at 1. That means right hand derivative exists and is equal to 5. So we know this fact for sure about the right hand derivative. Now if you look at this expression here, h tends to 0, denominator is tending towards 0. So if the numerator is non-zero, if the numerator is non-zero, then you know that non-zero by 0, that is if you have a non-zero value in the numerator and the denominator approaches 0, then that limit does not exist. So since RHD exists, so since right hand derivative exists, this implies that b minus 2 minus a has to be 0, because in that case you get indeterminate form, 0 by 0 form, which you know that limit will exist. So b minus 2 minus a can never be 0, non-zero here, because this limit, right hand limit exists, we know that. So b minus 2 minus a has to be 0. So from here you have b minus a equal to 2. So suppose this is 1. Okay. Now, uh, so right hand derivative exists from here. We right hand derivative exists from we get this relation, and from the second clue, that is right hand derivative is equal to 5. From there, I can say that uh, since b minus 2 minus a is 0, my right hand derivative is just b now. So b equal to 5. So this last part is very important. I am repeating once more that in order this for this limit to exist, I must have the numerator 0, otherwise the limit will not exist. So this is one condition we get, that b minus a equal to 2. And now what happens to the right hand derivative? Since this portion has become 0, the entire right hand derivative is just b, right? But we know that the right hand derivative equal to left hand derivative, so b must be equal to 5. So now if you substitute b equal to 5 here, you get the value of a. Substituting this, we get a equal to 3. So that's the answer. A equal to 3, b equal to 5. Okay, so I'll end the video here on differentiability. I think it has become quite long, but again, I had to omit many sums. If you have any queries, any difficulties, please write to me either here in the YouTube channel itself or in the group, WhatsApp group, or you can mail me, whatever you want to. Okay?